right, so we talked about this yesterday. A function is a set, they use D and R for domain and range, is a set D to a set R. There's a rule that every value in the domain is different. So maybe you could write here, all x's are different. And the input values, or the independent variable, is always called the domain of the function. And what you get out of that, the output values are called the range of the function. I think you feel pretty good about those today. Domain and range. I'm hearing them for a while. That's good. This is going to be a piece cake. So how about this one? This is a lovely little multiple expression. Don't all yell at once. You're going to be so excited. Of the three graphs shown below, which is not a function? Jesse. Because why? Oh yeah, like if we went through right here, right? And we kind of talked about this yesterday, about that vertical line test. And the vertical line test is a great way to check to see if the x's repeat themselves. But just know at some time in the future, I'm going to ask you to explain to me why the vertical line test works. So it's because, why again? Can someone tell me why the vertical line test works? Yeah, to tell if it's a function, there can only be one x value for every y. So if your vertical line has more than one point, it means there's more than one x value. So vertical line test is a great tool, but just make sure you understand why it works. I'm going to make you tell me. There's some questions on your homework today that you just have to say, is it a function or not? That's what you do, right? But then the rest of your homework is going to be the way. I think 3. I think that's always. Okay, so here's where the next section, I think, after this one is the functions, the types of functions reviewing. So if you don't remember all the state, again, it's going to be okay. But when we have a test in here over this chapter, this is only 1-2. There's like 6 sections, so there's a long way to go. We're going to get better at knowing what this graph looks like. So when you see a square root graph, I don't know if in your head you think, oh, I know the shape of that's going to be a... Oh, it says this. We did one on our little chart thing, right? I like to say it's half of a parabola on its side, because it's not the whole parabola on the side, right? Or it wouldn't be a function. So it's half of a parabola on its side. If you don't know, you could always pick some points here, right? What's a good number I could pick for x here? I like -1. I like 2. Why is -1 a good number to pick? And if I plug 2 in there, 2 plus 2 is 4. And square root of 4 is 2. I could plug 7 in there. 7 plus 2 is 9. What's the smallest number I could plug in? Could I plug -10 in there? What happens when I plug -10 in there? We graph the square root of -8? Where would you graph it? It's imaginary, right? So although we know how to deal with imaginary numbers, we don't graph imaginary numbers. Okay. No. So, complex numbers, we can't graph those, all right? So that's where this whole idea of domain and range comes into play. You have to think about the domain is what x's are allowed. I think it's easier to think about what x isn't allowed. I can't have a negative underneath that square root. So what is the smallest number I can have under that square root?
Square root of 0 is always split.
No, you square root 0 is 0. Is it 0 squared equal to 0? So you can square the square root of 0 is just 0.
No,
0 is a real number. I think we're gonna. You two can't sit right. Tomorrow or Monday, we're gonna end this. When you have a square root function, I'm just putting a square root symbol, you have to know that you can't have anything smaller than 0. You can have 0, but you can't have anything smaller than 0. So to find the domain of a square root function, if you just set what's underneath it greater than or equal to 0, you'll always get the domain, or you'll always get that starting number if you're not sure what that is. Negative 1, 1, 2, 2, 7, 3, negative 2. And again, without a calculator, by the time we have a test in here, I expect that you know that general shape, that it's kind of a half of a parabola on its side, that you're not going to connect this with rough, jagged edges. It's a nice smooth curve, starting here and going like that. Just like that one on the little poster there. So one way that you can use domain and range is you could always just make an XY chart and graph it, and if you graph it correctly, you should be able to look at it and tell me where do the x's start or stop, where do the y's start or stop. But eventually, we want to get to the point that we don't have to graph it every time, and so that's where I could just say on this one, if I was going to find the domain, I could just set what's under the radical greater than or equal to 0, and I could get that the x values are greater than or equal to if 2. And that's what shows on my graph, right? It starts at negative 2 and goes to the right. You have two options of how you're going to write your domain. You can write it in set notation, where you would say the domain is all the x's such that x is greater than or equal to negative 2. Have you seen that before? The better option, I think, is to do interval notation, which would be, I could say, starting at negative 2, including negative 2, going to infinity. I'm pretty sure your online homework wants that. Your textbook wants that. Like, higher math, this is what they do. On a test, I would count this right too, and we'll talk about sometimes the domain is a mess. And this is a little easier than writing like 7 intervals. But we're not getting that ugly yet. But just know that I'm pretty sure your homework wants you to do this, and so just you want to practice putting those interval notations in. And then the range. The range is the y value. So again, if it's graphed, you should be able to look at this and tell me where does the y start or stop, and is it going towards infinity or is it going towards negative infinity? And you're supposed to answer that. What's the lowest y value on this graph? Right? And that should make sense, because if there's nothing outside of this radical, we can't get anything smaller than 0 out of there, because the square root's always positive. And so my range is starting at 0 and going towards infinity. Very slowly, but it's going towards infinity. So I could say that my y or my range is greater than or equal to 0, or what would that be in interval notation? 0 to infinity. Another way, if you didn't have a graph, a really great way to know where your range starts is think about where your domain starts and what the y value is that goes with it. So you see what happens when it's going to -2? What do we get? So that's why our range starts there, but you still have to know whether it's going positively or negatively. So that's a positive square root, that's how I know it's going up. If there was a negative out front, then that means it would be the bottom half of this. It will be going to negative. So again, graphing is okay for now, but know that hopefully maybe eventually we won't have to that. So. Ooh, what about this one? Fractions are our friends. Not food. I love fractions, but people really, really hate them. And because they hate them, when they see them, they just like skip them. It's like, well, that's fraction.
I like the ones that like
Yeah, I have a secret. What about this? This was like second semester algebra 2. You graphed these things called rational functions. Do you remember what they look like? Yeah, I like to say they look like this.
oh, no, those are
Like, one side goes like this. One side. They have vertical asymptotes, horizontal asymptotes. We can make an X by chart here too if you want. It is like. I usually just wing this one, but I'm going to graph it nicely to jog your memory. I can say sketch it. You can make it sketch it graph. What happens if I pick 0 for x here? I can't do that one, right? Nope, you can't divide by 0 ever. It's not defined. I had a discussion with two parents on my son's football team about why you couldn't divide by 0. And right, think about if you had $12 and you want to split it between 3 people, you take 12 divided by 3. Right? Oh, wait, I know. But if you had $12 and you wanted to divide it into 0 people, you can't do that. Like, you can't. You can take 12 divided by 1, you give people 12, but you can't take $12 and divide it into 0. Doesn't make sense. But what happens when I pick 1? I get 2 over 1, which is 2. If I pick 2, I get 2 over 2, which is 1. If I pick 3, I get 2 over 3, which is 2/3. If I pick 1,000, I don't want it to reduce, so I'm going to pick. If I pick 1,001, I would get 2 over 1,001. If I picked 1,000,000, I would get 2 over 1,000,000. What is that getting closer and closer to, but not ever actually reaching? It's getting closer to infinity?
0.
Right, but this axis, if I keep going out on the x-axis, I keep getting closer and closer to 0, but not ever getting there. And that's where we get that shape. So like at 1, I get 2. At 2, I get 1. Then I get 2/3. And then I just keep getting closer and closer and closer without ever touching it. And that's where you get that asymptote. And Christian was already going the other way. If we picked fractions here, if we picked like 1/2, 2 divided by 1/2 is 4. We picked 1/8. You get 2 divided by 1/8, which is 16, and they just keep getting bigger and bigger and bigger, going towards infinity. So that's why this side, over here, kind of scary at first, but I love rational functions because I only pick a couple points and then I just follow the asymptotes. And the same thing's going to happen on the negative side, except for now that x is negative. So I'm going to get all these same numbers, except for they're going to be negative. So at -1, I get -2. At -2, I get -1. And again, as I go further and further out, I'm going to get those fractions closer and closer to 0. And then this way, I'm going to get further and further towards negative infinity. So we get those little, some people call them C-graphs. I just like to move my own like this. Because it's the second time you heard it. It's better. You learn better the second time. So here's the thing about domain and range. You could look at this and say what x's are allowed or aren't allowed, but you can also look at this equation in our xy chart, and what x value can we never plug into this problem? Can we plug every other x value in there? Yeah, because it goes all the way out here to infinity, all the way out here to negative infinity, but we can't plug 0. So this is where you have to write everything but 0. So this is where some people really like set notation, because you can just say all x's such that x cannot equal 0. Right? People like that. In interval notation, you have to say all real numbers except for you skip over 0. So that becomes like a or interval. So you could say negative infinity up to 0, not including 0, union, start back right after 0 to infinity. So if you have an asymptote and you're writing it in interval notation, which I'm pretty sure is what the online part wants you to do, you have to just skip over it. So think about if you had 2 asymptotes, you'd have to skip over both of them, and that's where people are like, I'd rather do set notation, which is why I'm okay with you writing set notation on something like this. What about the y values? Do I get all the y values, or are there any excluded as well? I also can never get 0 for y. You could just think about it like this, like what value can I plug in for x that I could get 0 for y? I can't. There are rules for horizontal asymptotes that we'll talk about tomorrow, but basically there's a horizontal asymptote at 0 as well. So the easy way would be able to say where y can't equal 0, or the range is exactly the same interval from negative infinity to 0, union 0 to infinity. So we've looked at 2 functions that the domain and range are restricted. But I want you to remember that most of the functions you've dealt with so far in your life have nice continuous domains and ranges. So I just want to throw in an extra one here to remind you that if I gave you this lovely function, I don't expect that you graph this. Remember that whole fun game, CRT, synthetic decision and long decision, and that. This would not be that much fun to graph, to know like the max and the mins and all that stuff. Is there any x value I'm not allowed to plug in here? There's nothing in the denominator, there's no square roots. If there's nothing that says I can't plug a number in there, I can't divide by 0 because there's no fraction, that means the domain is all real numbers. So don't let that one trick you, because sometimes we spend so much time talking about the restricted domains that we forget that all polynomial functions have a domain of all real numbers. And this is how I think it's best to write all real numbers. If you want to write this in set notation, you have to say all x's such that x is a real number, which you could write that out, or do you know the symbol for real numbers? Yeah, so you can do this fancy E. Do you know the fancy E? You can do a fancy E. X is an element of, and then it's like an R with 2 bars. So I'm going to take it like that. It's like a different language, right? And I just always make 2 lines and then make my arrow. But I don't know. It's just a symbol for real numbers. Complex numbers is the same way. Like complex numbers, you do that. I don't know. Z is for integers and Z is like that. I don't. It's just a symbol. What about the range here? How do you remember how to tell whether a polynomial function, like if the arrows both go up, if the arrows both go down, or if the arrows one goes up, one goes down? So what about x squared functions, quadratic? How do their arrows always go? X squared goes like this, right? What makes x squared go like this? What do you think about if it's x cubed? So it's all about even or odd, and we'll talk about this more this next week maybe? I don't know. If it's an even function, both arrows go up or both arrows go down. If it's an odd function, one arrow goes up, one arrow goes down. Could be this way if it's negative, it's leading coefficient. But the big thing to know is if it's an odd function and one arrow goes up and one arrow goes down, what's the range of that going to be? Is there any y value that won't be? Yeah, like it could be something like this, which means all real numbers for the range as well. Quadratics don't have a range of all real numbers because they're like this, right? Like they stop at some point. But cubics have a range of all real numbers. So we can say or y such that y is a So another thing that we want to talk about that maybe I don't know that you talked about in Algebra 2 is talking about continuous functions and not continuous functions, or points of discontinuity. That's a word you probably haven't said before. A continuous function, the book does a great definition of saying a continuous function is a function you could graph without ever lifting your pencil. So if you could make a graph without ever lifting your pencil, then that is a continuous function, right? That's a good definition. But there are types of functions that are not continuous, and they have special names of their discontinuities. So this one has a little hole in the graph. Did you talk about holes in the graph last year? This one has a hole in the graph, but then that hole's filled in up here. We call this a removable discontinuity. And the definition of a removable discontinuity is the discontinuity can be filled in with 1 point. And you don't have this magic button on yours, but if I took this little dot and I moved it up here, it would fill it in, and then it becomes continuous. And so that's what it means by being removable. So I'm going to just write here, can be filled in by 1 point. You have nothing to write all that on your paper? This one is also removable, and you might say it's the exact same graph, but the difference is it doesn't have a little dot up there. This is just a hole in the graph, but you could still fill it in with 1 dot with your pencil. So this one's also removable. Sean likes this one best, right?
Yep.
This is not removable, because even if you fill this dot in, there's still this gap where you'd have to pick your pencil up. This one is called a jump discontinuity, and that's easy to remember because there's like a jump or a gap in the graph. You have to jump from one point to the other.
Well, give us
jump is not really big. Well, because it's not continuous, so it's discontinuous.
Because stop is
This has an asymptote, so it's also not continuous. You have to pick up your pencil over the asymptote. We call this an infinite discontinuity because asymptotes are infinite. Right? That discontinuity kind of goes on forever in both directions. So here we go. All that talk, and now this is a really easy question. Which of the following figures shows functions that are discontinuous at x equals 2? And now it might be really hard to see that on your paper. I don't know. This one, you never have to lift your pencil up. But this one, right there at x equals 2, there's a hole in the graph. So this one is not continuous at x equals 2. And what kind of discontinuity would that be? Removable. And I always want to put an E in removable, but apparently it's not. Okay, I really have 2 more things, but I might stop for extreme. I know that you probably can recognize when a function is increasing, decreasing, or constant, but again, we want to practice writing the intervals for that. So, these are the very mathematical definitions that Justin's going to love of this, but then I'm going to help you think of it in a different way. But it says a function is increasing on an interval if, for any 2 points in the interval, a positive change in x results in a positive change in f of x, which is y. Just means like as x gets bigger, y gets bigger. To me, I always think about increasing, it looks like the graph is going up, right? So here to here, right, that would be an increasing function. As x is getting bigger, y is getting bigger. Or if you're reading that graph from left to right, it kind of looks like you're walking uphill, right? A function is decreasing on an interval if for any 2 points in that interval, a positive change in x results in a negative change in y, or f of x. Which means as x is getting bigger, y is actually getting smaller. You could even think linear here if you want, right? A linear function that's decreasing. As x moves to the right, the y values are actually getting smaller. Or again, reading left to right, it looks like you're going down that hill. And we don't have this one very often, but we also can have a constant function. And it just means as x changes, y does not change at all. That would be like a flip slope. Like this, right? Like you're walking along a floor that's supposed to be left. But because this is precalculus and not algebra 1, algebra 2, we're not just going to say increase and decrease is constant. We're going to give the interval. It's an interval notation. So let's look at one more example and then I'll stop. I never know if these are supposed to be going on forever or I'm supposed to stop at -5 and 5 on here, so that's kind of the big thing. I'm not sure how it's going to save this here. But on this one, what would you say about this function? It's increasing the entire time. So if we went by what's just showing, we could say it's increasing from -5 to 5. Maybe we want to include 5, maybe we don't want to include 5. There's a big debate in calculus about whether you include the increase or don't include the increase. I think it's a big debate. If you want to say there's arrows on this, you would say it's increasing negative infinity to infinity. Right? So it just depends on how you interpret that graph. Does it stop at 5 or does it keep going? Right. I think I like to say there's arrows on it. What about this graph? It's decreasing the entire interval. So we could say decreasing from -5 to 5. Just kidding. Decreasing negative infinity to infinity. We said there's arrows on it, so just stop. And again, when you're talking about increasing and decreasing intervals, we're talking about the x values. So we're talking about this one. And this would be a nice little example of a constant function that's constant the entire time. But on your homework, they're probably not going to be always increasing, always decreasing, or always constant. That would be too easy, right? Your functions are going to look more like this. So we could see here it's decreasing, it changes the constant, it changes the increasing. If this were algebra 2, you could probably just write on there and get your points. But pre-calculus, you have to write it out. That it's decreasing. Whoa! Look, it just appeared. Whoa! I wonder if all these appeared. Oh, look at this. Magic trick. And again, we're saying that there's arrows here. So we would say it's decreasing from negative infinity to negative 2. And again, notice that the book, these are the book answers, they included the endpoint. I always struggle including the endpoint because my argument is how can it be decreasing at negative 2 and constant at negative 2? So that's why I like to use the parenthesis, but apparently the book's using the endpoint, so just you see my logic? I'm guessing if the book is using brackets, you should use bracket. Or we'll mark it. In calculus, on the AP exams, they count it either way, because there's this argument about what they use it in. And so that's what we're looking for there. Okay? Alright, so we're going to stop. I had one more example over increasing and decreasing. And I had talking about max and min versus absolute versus local. There's a couple of questions that you don't work about max and min. Try to pick one or go through them and we'll talk about it tomorrow. Okay? I keep thinking today's Friday, but it's not. No.